back, everyone. Today, we're diving into the fascinating world of Newton's laws of motion. It's incredible how these fundamental principles govern everything from the way we walk to how rockets launch into space. So, let's kick things off with Newton's first law, which states that an object stays still or keeps moving at a steady pace in a straight line unless an external force makes it change. This is also known as the law of equilibrium when forces are balanced.
Wait. So you're saying that if I just, throw a ball in space, it would just keep going forever? Sigh.
Exactly! In the vacuum of space, there's no air resistance or friction to slow it down. It's like when you slide a hockey puck on ice. It keeps gliding until it hits something. That's the beauty of inertia.
Oh wow, that's so cool. So if I were to push a shopping cart, it would keep rolling until it hits a wall or something. Laughs.
Right, and that's where the concept of force comes in. A force is essentially a push or a pull. When you push the cart, you're applying a force that overcomes its inertia.
So what about when I'm trying to push a heavy cart? It's way harder, right? Sigh.
Absolutely! That brings us to Newton's second law, which tells us that acceleration depends on two factors, mass and force. The formula is a E-F-M, meaning that the force applied is directly proportional to acceleration, while the mass is inversely proportional.
Oh, I see. So, if I had a cart full of bricks versus one full of feathers, the brick cart would be way harder to push. Laughs.
Exactly. And that's why we measure force in newtons, named after Sir Isaac Newton himself. It's fascinating how mass tells us about an object's resistance to changes in motion or its inertia.
Right. And what about weight? Is that different from mass? Sigh.
Great question. Weight is the gravitational force acting on an object. So, while mass is a measure of how much matter is in an object, weight depends on the gravitational pull acting on that mass.
So if I went to the moon, I'd weigh less because the moon has less gravity? Laughs.
Exactly. You'd weigh about 1/6 of your Earth weight. It's a wild thought, isn't it? Now, what about Newton's third law? I've heard it's all about action and reaction, right?
Wow, that's mind-blowing. So what about Newton's third law? I've heard it's all about action and reaction, right? Sigh.
Yes! For every action, there's an equal but opposite reaction. Think of it like this. When you jump off a small boat, you push down on the boat and it pushes you up into the air.
Oh, that's like when I'm on a trampoline. I push down and then I bounce back up. Laughs.
Exactly. And this principle is crucial in understanding how forces interact. It's not just about one object, it's about the relationship between them.
So if I'm pushing against a wall, the wall is pushing back at me? Sigh.
Precisely. That's the beauty of action-reaction pairs. Now, let's talk about friction. Friction is a force that resists sliding motion between touching surfaces.
So when I try to slide a book across a table, it stops because of friction? Laughs.
Exactly. Friction is caused by microscopic grooves and ridges in the surfaces of the objects. It depends on the normal force, which is the force pressing the surfaces together, and the coefficient of friction, which measures how rough or smooth those surfaces are.
So if I had a super smooth table, it would be easier to slide the book? Sigh.
Yes, and that's why we can reduce friction by using lubricants or even sandpaper to smooth out surfaces.
Wow, I never thought about it that way. So what about when things are in motion? Laughs.
Great segue! When objects are already in motion, we deal with kinetic friction, which is less than static friction. It takes more energy to get a stationary object moving than to keep it moving.
Oh, that makes sense. It's like when I'm trying to get my car moving from a stoplight, it takes more gas to start than to keep going. Sigh.
Exactly. Now, let's shift gears to linear and rotational motion. Linear motion is straightforward, while rotational motion involves an object moving in a circular path.
So like when I'm spinning around in a chair? Laughs.
Yes, and that's where concepts like centripetal acceleration come into play. It's the inward acceleration that keeps an object moving in a circle.
Oh, so if I'm spinning and I let go, I'll fly off in a straight line? Sigh.
Exactly. That's because the centripetal force is no longer acting on you. It's fascinating how these principles apply to everything from roller coasters to planets orbiting the sun.
Wow, I can't believe how interconnected all of this is. So what about rockets? How do they fit into all of this? Laughs.
Great question. A rocket accelerates upwards due to the thrust generated by its engines, which push hot gases downwards. This creates an equal and opposite reaction that propels the rocket upwards, perfectly illustrating Newton's third law.
So it's like the rocket is pushing against the ground and the ground is pushing it up? Sigh.
Exactly! And that's why understanding these laws is crucial for everything from launching rockets to predicting planetary motion.
Wow, this is so much fun. I can't wait to learn more. Laughs.